Hello everyone. This chapter focuses on the technical principles of MapReduce and Yarn. After this course, we'll be able to know concepts of MapReduce and Yarn, application scenarios and principles of MapReduce, functions and architectures of MapReduce and Yarn, and also I'll talk about some new features of Yarn. First, let's take a look at the introduction to MapReduce and Yarn. Well, MapReduce is a processing technique and a program model for distributed parallel computing of a massive dataset. The advantages of MapReduce include that it's easy to program. Programmers only need to describe what to do, and the execution framework will do the job accordingly. And it's easy to scale data processing over multiple computing nodes. We can just simply add nodes to improve cluster capabilities. Besides, MapReduce is highly fault-tolerant. If one of the nodes in the cluster fails, tasks running on the node can be performed on another node using computer migration or data migration to ensure successful execution of tasks. And Yarn, yet another resource negotiator, is Hadoop's Cluster Resource Manager, providing resource management and scheduling for upper-layer applications. Why say another? Actually, there is a resource negotiator before Yarn, but it has many limitations, and it's not used anymore. So here I don't talk about it too much. Take a look at the architecture of Fusion inside Hadoop. At the bottom is HDFS, which is the storage infrastructure. On top of HDFS is Yarn, which is used for managing and scheduling resources for applications. Then, there are some computing engines above Yarn, like MapReduce, Spark, and Hive. When these computing engines are working, they need to apply resources from Yarn. So in this case, administrators do not need to maintain resource manager for each computing engine. They only need to maintain Yarn, which reduces the operation and maintenance cost. Besides, the whole cluster shares the resources so that they can be highly used. Then, let's take a look at the functions and architectures of MapReduce and Yarn. How does the process of MapReduce work? Let's take a look. At first, MapReduce submits requests to Resource Manager. Resource Manager is responsible for the unified management and allocation of all resources in the cluster. It's a component of Yarn. Then, Resource Manager creates jobs. But before jobs are submitted, the files to be processed need to be split. MapReduce regards a block as a split by default, and the client applications can also redefine the mapping relation between blocks and splits. For example, assume that a file is stored as 3 blocks in HDFS. When we use MapReduce to process this file, the file will be divided into 3 splits. Each block corresponds to a split, and each split corresponds to a map task. That is, a map task can only process a split. The number of splits determines that of map tasks created for the job. And after the jobs are submitted to Resource Manager allocates resources for them. It selects an appropriate node manager in the cluster to schedule application masters based on the workloads of node managers. Here, node manager is the agent on each node, and application master is responsible for all the jobs within the application lifecycle. So after a node manager is selected, application master initiates jobs and applies for resources from resource manager, and the selected node manager will start the container for task execution. Then is the process of map task. The map task takes a set of data and converts it into another set of data, where individual elements are broken down into key value pairs. Each map task has a circular memory buffer that it writes the output to. The buffer is 100 MB by default. The size can be configured by user. When the contents of the buffer reach a certain threshold size, which by default is 80%, data in the buffer will be written to local disks. Before it writes to disk, the following process must be completed. First, data is divided into partitions. The number of reduced tasks is determined by clients, and the number of partitions is determined by that of reduced tasks. And data with the same key value are sent to the same reduced tasks for processing. Within each partition, map output will be sorted by key, combined if necessary, and merged as a mapout file. Each time the memory buffer reaches the spill threshold, a new spill file is created. So after the map task has written its last output record, there could be several spill files. Before the task is finished, the spill files are merged into a single partitioned and sorted output file. This file is the mapout file. When map tasks are finished and the output progress of MOF reaches 3%, the reduced tasks are started and copy MOF files from each map task. The reduced task needs the map output for its particular partition from several map tasks across the cluster. The map tasks may finish at different times, so the reduced task starts copying their outputs as soon as each completes. Then, reduced tasks sort and merge multiple mapout files into one. During the reduce phase, the reduce function is invoked for each key in the sorted output. The output of this phase is written directly to the output file system, typically HDFS. Here, let me add another concept called shuffle. It's the data transfer process between the map task and the reduce task, which involves that reduced tasks copy MOF files from the map tasks and then sort and merge MOF files. Let's take a typical program word count as an example to better understand the working process of MapReduce. This program defines its own map and reduce functions that can analyze the times of each word repeated in a file. So for example, when we use the word count program to count the number of each word repeated in file A, the process is as follows. First, we need to make sure that file A to be processed is stored in HDFS and divided into blocks A1, A2, and A3, which are stored on data node 1, 2, and 3 separately. Then, the program submits applications to Resource Manager. The Resource Manager creates jobs based on the request and creates 3 map tasks as well as 3 reduced tasks that are running in containers based on the number of blocks. The output of map task is an MOF file that is partitioned and sorted but not combined. And then reduced tasks obtain the MOF from map tasks after combination, sorting, and user-defined reduce function processing. The output result is shown in the table 4. Let's see the detailed process of map task and reduce task. This figure shows the function of word count program. This is the result that we want. Assume the file that contains words is stored as 3 blocks in HDFS. So there are 3 map tasks based on the number of splits. Each map task generates an output like this in key-value pairs. And then we combine the results in each map output and do the shuffle, which is to copy MOF from map task and sort, merge into one file like this. And then use user-defined reduce functions to process the reduce input. That finally creates a reduced output. Next, let's see the architecture of Yarn. It consists of the following components: client, resource manager, node manager, application master, and container. Client is to submit jobs to resource manager. A resource manager is used to manage the use of resources across the cluster. There is only one resource manager in a Hadoop cluster. And node managers are running on all nodes in the cluster to launch and monitor containers, which also report node status to resource manager periodically. Application master is responsible for negotiating resources from the resource manager and working with the node manager to execute and monitor the component tasks. And a container is an abstraction of Yarn resources, and it executes an application-specific process with a constrained set of resources, including memory and CPU. And it reports the status of MapReduce tasks to application master. So when a client submits a job to resource manager, the resource manager receives the job and allocates the first container for the application program and asks node manager to start application master in the container. Then application master registers with the resource manager so users can directly view the operating status of the application programs. After that, application master applies for and obtains resources from resource manager in pooling mode using the RPC protocol for each task and monitors the tasks until finished. Once obtaining resources, application master asks node manager to start the tasks. Then, node managers start the tasks. Each task uses RPC to report its status and progress to application master, so that application master can restart the task if one fails. During the running of the application program, users can use RPC to obtain the operating status of the application program from application master at any time. After the application program ends, application master cancels its registration with the resource manager and closes itself. So this is the whole task scheduling of MapReduce on Yarn. Resource Manager in Yarn also uses an active standby architecture, which ensures high availability. Similar to the HDFS HA solution, when the active resource manager fails, the failover can be triggered automatically or manually to switch active and standby states. When automatic failover is not enabled, administrators must run a command to manually switch one of the resource manager nodes to the active state. When the active resource manager goes down or becomes unresponsive, another resource manager is automatically elected to be the active node that then takes over services. In Yarn, application master may break down, exit, or shut down for various reasons. If an application master goes down, resource manager will close all the containers that it manages, including containers where tasks are running, and the resource manager will start a new application master on another computing node. But for services that run for a long time, users do not wish the whole service stops because of the failure of an application master. Therefore, Yarn supports the feature of preserving the container status when starting a new application master so that the tasks in these containers can run continuously without any failure. Next, let's take a look at resource management and task scheduling of Yarn. Now, Yarn supports management and allocation of two types of resources, memory and CPU. Users can configure the memory and the number of CPU for each node manager. The first configuration indicates the physical memory size of the container running on node manager, expressed in megabytes. The value must be smaller than the memory size of the node manager server. And the second one indicates the ratio of the maximum available virtual memory to the physical memory of a container. The assigned container memory usage is specified based on physical memory. The proportion of virtual memory utilization exceeding the assigned value is not allowed to be greater than that ratio. And the third one indicates the number of CPU cores that can be allocated to a container. It's recommended that this parameter value to be set to 1.5 to 2 times the number of CPU cores. Let's see how the resources are allocated by Yarn. Well, in Yarn, resource schedulers organize resources through hierarchical queues. This ensures that resources are allocated and shared among queues, thereby improving the usage of cluster resources. To be more specific, Resource Scheduler in Resource Manager maintains information of a cluster of queues. Users can submit applications to one or more queues. Then, Resource Scheduler selects a queue based on certain algorithms and selects an application in the queue, and then attempts to allocate requested resources to the application. Here, queues are subsets of the whole cluster resources. Queues are classified into parent queues and child queues, or we can say leaf queues. A parent queue can have multiple leaf queues. Tasks are running on leaf queues. If a queue is specified when a task is submitted, the scheduler allocates the task to the queue. If no queue is specified, the task is allocated to the default queue. If resources fail to be allocated to an application due to the limit of some parameters, the resource scheduler will select the next application. After the scheduler selects an application, the application may manage many resource requests. The scheduler first satisfies the request for local resources, and then for resources on the same rack, and finally for resources from any machine. The capacity scheduler is designed to run Hadoop applications as a shared, multi-tenant cluster in an operator-friendly manner while maximizing the throughput and the utilization of the cluster. Traditionally, each organization has its own private set of compute resources that have sufficient capacity to meet the organization's service level agreement under peak or near-peak conditions. This generally leads to poor average utilization and overhead of managing multiple independent clusters. The capacity scheduler also provides a strict set of limits to ensure that a single application or a user or a queue cannot consume disproportionate amount of resources in the cluster. Administrators can restrict the resource used by a queue, user, or a job. The capacity scheduler supports the following features. Capacity assurance. All applications submitted to a queue will have access to the resource capacity allocated to the queue. Administrators can configure soft limits and optional hard limits on the capacity allocated to each queue. Flexibility. Temporarily, resource supplies of a queue can be shared with other queues. However, such resources must be released in case of new application submission to the queue. Such flexible resource allocation helps notably improve resource usage. Priority. This feature allows applications to be submitted and scheduled with different priorities. Higher integer value indicates higher priority for an application. Currently, application priority is supported only for FIFO ordering policy. Multi-leasing. Comprehensive set of limits are provided to prevent a single application, user, or queue from monopolizing resources of the queue or the cluster as a whole to ensure that the cluster is not overwhelmed. Dynamic update of configuration files. As the administrator, you can dynamically modify configuration parameters as required to achieve online cluster management. There are two steps for task selection by capacity scheduler. The capacity scheduler selects an appropriate queue first and then selects a task from the queue. The queue is selected based on the following policies. The queue with the lower resource usage is allocated first. For example, you have two queues, Q1 and Q2, and both have the same capacities, let's say 30, and the used capacity of Q1 is 10 and Q2 is 12. Then, resources are allocated to Q1 first. Resources are allocated to the queue with the minimum queue hierarchy first, and the resources are allocated to the resource reclamation request queue first. A task is then selected based on the task priority and submission sequence as well as the limits of user resources and memory. In Fusion Insight Platform, users can create queues by Fusion Insight Manager. Here shows a web page of tenant management in Fusion Insight Manager. When creating a tenant and associating with Yang, a queue with the same name as tenant will be created. Log into Fusion Insight Manager and choose Tenant, Dynamic Resource Plan, Resource Distribution Policy. We can see the following page. The resource allocation area shows the resource capacity for each queue. The resource capacity of queues can be configured by users. By default, the capacity of the default queue is 20% of the total cluster resources, and the capacity of the new queues is 10% of the total cluster resources if user does not modify the default configuration. And there is a shadow queue in the background. A shadow queue is named XXDefault, which is invisible. The remaining resources of the cluster are allocated to this queue. The resources used by a queue may exceed its capacity due to resource sharing. The maximum resource usage can be limited by parameter, which is set to 100 by default. For example, if the maximum capacity of QA is set to 100, and there are only tasks running in QA, theoretically, QA can use all the cluster resources. Besides, Yarn supports to limit users and tasks. We can configure the user and task limitation parameters by Fusion Insight Manager in the QConfig page. While for user limitation, which indicates the resource usage restrictions for users, there are two parameters. First is minimum resource assurance of a user. When there are multiple tasks of different users running at the same time in a queue, the available resources for each user is between the minimum value and the maximum value. The maximum value is determined by the number of running tasks, and the minimum value is determined by this parameter minimum user limit %, which is set by users. For example, let's set this parameter to 25 for QA. Then, when first user submits jobs to QA, he will obtain 100% of the resources in QA. And then, second user submits jobs. Each user will obtain 50% of the resources at most, and then 33.3% at most when the third user submits jobs. If this continues, when the fifth user submits jobs, he cannot obtain any resources and must wait for them to be released by other users, because this parameter ensures that each user can obtain 25% resources at least. And the second parameter is maximum resource usage of a user, which means the multiples of queue capacity. For example, if we set this parameter to 1, which is by default, the resource obtained by user cannot exceed the queue capacity. Remember that the resource obtained by a user can exceed the resource capacity, but must not exceed the maximum capacity. As for task limitation, there are three parameters. Maximum number of active tasks. The default value is 10,000. When the number of submitted task requests reaches 10,000, new tasks will be rejected. Second is maximum number of tasks in a queue. The default number is 1,000. If the number of submitted task requests in QA reaches 1,000, new tasks will also be rejected. And third is maximum number of tasks submitted by a user. This parameter depends on the maximum number of tasks in a queue. For each user, the maximum number of tasks submitted is the product of three parameters, which is the maximum number of tasks in a queue, minimum resource assurance of a user, and the maximum resource usage of a user. After configuration, users can view the information queue by Fusion Insight Manager Web UI. This figure shows the information of QA, including used capacity, configured capacity, and so on. The last part is the enhanced features of Yarn in Fusion Insight. First one is dynamic memory management. This feature is used to optimize the memory usage of containers in Node Manager. While in earlier version of Yarn, Node Manager will queue the containers that exceed the container's memory threshold, even though total configured memory utilization of the node is low. As a result, consumer jobs fail frequently. So in order to improve this, Fusion Insight adds another judgment method, which is to queue overused container only when the overall memory usage of all containers in Node Manager reaches a certain threshold value. This value is the memory threshold set for Node Manager, which can be calculated as follows. The other one is label-based scheduling. Before label-based scheduling is used, it's impossible to control which node a task is submitted to. Tasks are allocated to nodes based on some algorithms and conditions. Label-based scheduling can specify the nodes to which tasks are submitted. But there are some scenarios that applications may need special computing resources. For example, there are applications that have demanding memory requirements, but due to uncontrollable task submission, these tasks may run on servers with standard performance. So in this case, Fusion inside Yang schedules tasks based on labels. Users are able to label each node manager, for example, labeling node manager with high memory or high I/O. In the meantime, users can label each queue in the scheduler. That is, queues are abundant with labels. Jobs submitted to a queue use resources on the labeled node, so tasks are running on labeled nodes. For example, those tasks that have demanding memory requirements will be submitted to queues with high memory labels, so that tasks can run on servers with large memory. So this chapter mainly talks about application scenarios and architectures of MapReduce and Yang, resource management and task scheduling of Yang, and also some enhanced features of Yang in Fusion Inside HD. Okay, that's all for MapReduce and Yang. Thank you.